Today's video I'm going to show you guys how to save data to the EEPROM of the Arduino at power down. So you want to do this for a couple of reasons. First of all, the EEPROM memory is 1 kilobyte in the Arduino, and that is in the 328P, and that is a separate memory from the program memory, something that I actually didn't know. The problem with this memory, unlike RAM, you can't write to it an infinite amount of times, right? So with the SRAM that's in here, you could basically erase it, write it, delete it, allocate it, so on and so forth, infinitely many times. It will not degrade. The EEPROM has the advantage that it retains all the information after power has been applied to it, so basically with no power. But you can only write, I believe, it says in the data sheet, 100,000 times at least, roughly in any case. Definitely in the real world, you will probably be able to overcome that limit, right, quite easily. But in any case, 100,000 times might seem like a lot, but for local variables that constantly change and so on and so forth, that really can happen quite quickly. The second reason why you would want to not use the EEPROM too much is because it's quite slow. So first of all, writing to it is incredibly slow and can take above 1 millisecond even. And reading is also not as fast as the SRAM in any case, right? So if you have something that is supposed to refresh very quickly, then you also should not use the EEPROM. So basically, the setup here is a demo for how to have a variable in the SRAM that will be lost at power down, and exactly while it's powering down, get that saved into the EEPROM so we don't lose it. And that's like saying a 5-word sentence in 5 minutes, but I hope it was clear enough. So let's get a quick demo going. So for this I might actually bring the brightness down a bit for the OLED. And this is a pretty simple demo. We just have a counter counting up. And again, what is cool is we detect power loss and save the data to the non-volatile memory. Basically, when fuck off appears on the screen, the data has already been saved. So just as a quick peek, we'll go into the schematic, how this is wired up, and the code a bit later. So yeah, this is pretty much all. If you don't want the cool goodbye message, you can actually get rid of this cap. So this is 4,500 microfarads. That's probably 4,000. It's like a 10-year-old cap from a TV. And it still works. So this has enough capacitance to detect the voltage drop. Even with the loads, there's enough time to actually save to the EEPROM. So let's get to 30. Boom. And it actually has saved it. So that is very cool. So minimal setup kind of only requires the small cap. And this can be, I mean, what is this? This is 22 microfarads, so I think you can go even lower because we're reading this with a 1 megohm resistor. I mean, this is going to be fine. Right, so let's try that again. And put the cap back. Let's try not to put it back the other way around. Is it still focused? It is. And it's working. And I also programmed the button to do something. I mean, I had it, so yeah, why not? And it's a cool little exercise to see overflow and underflow. Anyhow, so let's move on to the schematic. I actually got this. Okay, so this is a pretty crude schematic, but it should definitely bring the point across given that this is a very simple circuit. So yeah, basically what we have is the USB power coming in. So this is 5 volts, and this gets routed to the 5-volt pin and the ground pin on the board. And this is the only place we have access to, so we can't actually put a cap in between the USB power and the Arduino. This would be the actual elegant way of doing it. I'll show this at the end for those that have the ability. I mean, when I'll be building this into an actual circuit, I will do the good way, kind of. Do it the nice way. So exactly, so what's going on over here? So we first of all have a 10 ohm resistor going to the negatives of the caps, and this is here only to limit the rate at which these caps are charging. So if these are completely discharged, and we have the big one, right, the 4,000, what was it, 4,700 microfarads, if you just stick this across USB, it's not nice. It's going to be basically like putting a short circuit for a pretty brief period of time, but it will be a pretty big spike, and really don't want to fuck my Mac up with some random project. So and I think so even in the USB specifications, I think the most you can have is like 200 or 100 microfarads, so quite little capacitance across the USB rails. Anyway, so this 10 ohm resistor basically will at most let, I think it's 400 something milliamps at most. So we're going to be charging these at 400 milliamps, and it's going to decrease as the voltage in the caps increases. C1 is the big one here, and it is, as I've showed, not necessary. So this is just for added style, added elegance. And basically we could display a message for the amount of time it'll take for this one to completely discharge. I might actually change this with a super cap in the final build. I'm going to build a power monitor. So yeah. Anyway, this C2 though is the power loss capacitor. And basically what we're doing here is we have this diode so that when we want to charge the capacitor, you can imagine the electrons will go like this, right? From minus, we'll go through the 10 ohm, charge the cap, go through the diode this way, and then go back to the positive, and the cycle completes, kind of. When you remove the power, this capacitor here will not attempt to power the board. This one will. This one won't, because it'll be stopped by the diode. Right, so electrons will not be able to flow this way, right? We'll try to go this way through the Arduino and then come back to this diode, but it's not pointing the right way, so it's going to block them. So basically, at power down, this will continue to have 5 volts on it. It's actually going to be 4.5 because I think we have a half a volt drop across this diode. But yeah. It is what it is. It's and this also should have quite a bit less than 5 because there's also a diode here, but yeah, this is just details. So assume this has 5 volts after we've removed the power, so after we've unplugged the USB. So what's going to happen? This cap and all the capacitance that's on the board, I mean there are some capacitors on the nano board, will have their voltage slowly decrease. And what will happen is this voltage will be above the supply voltage of the chip. And this is illegal. This is the illegal part. This is the taboo part. This is the naughty thing we're doing. So the data sheet, I think, specs that you can only read 0.3 volts above your reference voltage. Right, so analog read basically gives you a value between 0 and 1023. That shows you where you are between 0 and the supply voltage. So if you give it 3 volts and there's 3 volts on A0, it's going to give you 1023. If you're at 6 volts and this is 6 volts, your analog read is going to give 1023. So it's relative to the positive supply rail, right? So what's going to happen is we're going to constantly have 5 volts here whilst our system voltage is going to drop. So all of a sudden we're going to see this A0 way above our head, right? We're going to be at what, like 3 volts? These chips work at, I think, down to 2.5. I've tested them quite reliably even. At the stock speed, if you underclock them, I think it's even lower anyway. So basically, immediately as we start losing power from this cap, we're going to have this plus be below the voltage that we see here. We're going to have like 4 volts here and 5 here, which again is going to be definitely more than 0.3 of a volt, which we can legally have on A0. which is why I've set up this 1 mega ohm resistor to limit any current that might damage the... It actually works without it. I mean, the first time I did it without it and it was fine, so But long term, I've done it like many times and really doesn't seem to affect it that much. Right, so I mean, it works. I don't know. If it's gonna stop working in like 500 tries, I'll let you guys know in the description, but I highly doubt it. So as a quick and dirty solution, this seems to work very reliably, superbly. So basically, the rule I have in the Arduino is every so often in the loop, I check, is A0 1023? Because usually, although you would expect it to be 1023, it is not going to be. Because if we have 5 volts here, right? We have 5 volts here, but we're going to have this this diode drop, which is going to eat away half a volt, right? So we're going to be reading 4.5 volts on A0 and have 5 volts as the system level. So we're going to be reading, I don't know, 950 or something, or 900 or something. So immediately, once the system voltage dips below 4.5, we're going to max out and overflow, and not overflow, but saturate our analog input. And we're going to be reading full-on, steady 1023. So the moment we read 1023, we can start our basically goodbye routine, so our power down routine, and save all the data and display something on the screen, or if not needed, then not. So with the schematic out of the way, let's quickly go over to the computer. I have a math exam tomorrow, so this is going to be quicker than the usual videos. Alright, so let's first take a look at the libraries that we'll be using. I'm including this streaming.h. This is completely not required, so to say. It's just for added elegance. I've actually seen this in an example done by someone, I think, for another EEPROM library, for an external EEPROM library. So kudos to that guy. I actually don't remember right now, for introducing me to this. Actually, it is very nice, and it does have absolutely no overhead. It doesn't add any overhead. Second, we need the EEPROM library, and this you have to download. I'll actually include the link in the description. This you don't have to download. It's automatically included with the Arduino IDE. The display libraries you have to download. This I'll link my other video, right, as I've previously mentioned, where I discuss all about wiring up one of these and using it. After this, quite little is happening, just some definitions for the button. Again, completely unnecessary. I actually had this for something else before and decided to leave it in. The counter and a timer. Furthermore, we do have the display that we're defining, right, this OLED object. So in the setup, right, for the new ones, this is the piece of code that runs once at startup, and then the loop, is the piece of code that runs infinitely many times. This is equivalent to a while true. So that being said, we're starting a serial monitor. We're not actually using it at the moment. We're assigning the button to be an input pull-up type, and that is basically, it internally connects it to a I forget how many ohms, but quite many resistors, so that if you have nothing connected to this pin, it reads high, and if you connect it, if you bring it low, it'll read low. So it's perfect for buttons. So basically, you tie the button to ground when you want it to be read as being pressed. We're initializing the display. Just right quick, right? We give it the address. We clear the display. We set the font, the size, and the type of the color, right? So this is white text with black background. And the fun starts. We read from the EEPROM, again at address 0, and this is byte addressed, so byte 1. Address 1, for example, would be the 9th bit up until the, 17th bit. No, is it? No, 15th. Is it? I'm talking out of my ass. So first one is 0 up to 8. no, 0 up to 7, and then it's 8 up to, is it really 16? Huh. That's 15. Yeah, I'm talking shit. So basically, address 0 is going to be bits. So yeah, this would be address 0, would be these bits. So bit 0, 1, 2, 3, 4, 5, 6, 7. And then address 1 will be bits 8, 9, 10, so on and so forth. And the last address is 10,023. And all right. So now that we got that out of the way, we clear the display again for some reason. As doesn't hurt, but anyway. We set the cursor, so basically where we want to start writing. It's the equivalent to clicking this, so we want to write in the middle of this sentence, we click the cursor and then we write exactly there. And we print using this C++ notation, so this is equivalent to OLED.print counter. So basically all of this is substituted by this. And it's cool because you can actually do this kind of stuff. Right? And it'll still work. And all of this is done with just cool definitions in line. So the library basically replaces all of this with the proper notation with the .print and so on and so forth. So it's very elegant and it adds absolutely no overhead, which is very sexy indeed. So we get to the loop. This will be rolling infinitely many times. All we have here is basically checking if the button is pressed or not. So if the button is pressed, we're going to be reading low. And every 100 milliseconds, so 10 times a second, we're going to decrease the counter. And if the button is not pressed, it's going to read high because of that internal pull-up. And we're going to increase the counter. We're going to clear the display, set the cursor, print the counter to the buffer, and then display the buffer to the screen, right? So what this does, what the print function does, is there's an array declared in the RAM of the Arduino with one value for each pixel, right? One spot, one boolean for each pixel. It might be more efficient though, but anyway. Basically what this does is it modifies that internal image of the display, right? So there's literally a copy of a virtual copy of the display that's in the memory of the microcontroller. So basically you're just modifying this over. We're deleting all of the values in that map, then we're putting some values into it, some text in this case, and then we're moving that over, shoving that over into the screen, kind of. And the screen will keep displaying that until told otherwise, is the way this works. And we're going to record the time so that we can do all of this every second or every 100 milliseconds. All right, and then this is what happens when we're losing power. We're going to be reading 1023, which is the maximum value on our analog 0 pin. We're going to be overloading the analog input. Again, naughty us. And yeah, basically we're just writing to the EEPROM, like first things first, we do what's necessary, right? Write to the EEPROM. Then we say goodbye, right? Whatever message you want to have. Like, I'm always going to have some swear words here because I don't know, I just find it highly amusing. And then we're going to wait basically until we die, right? So, I don't know. I don't want this to go out of here and then start messing with the counter again or whatever whilst the power is going down, right? Because we might end up corrupting I don't know. Who knows, right? I mean, I just want this to happen once at power down. Yeah, that's pretty much all. So hope you've enjoyed it, learned something, and yeah, have any questions, then hit me up in the comments. Although this is quite straightforward. All right, bye guys. Okay, so now for the correct way of doing it. If you can afford to stick some components between your power supply and your Arduino, then this is the way you should do it. So this also has a bit fewer components, so all the better. So basically we have this diode in circuit, right? And this will basically also double as a reverse protection diode. If you want current to flow, basically you want the diode pointing to the negative, right? So you have the electrons coming into the arrow, kind of, right? Okay. So when you have 5 volts here, this capacitor will be charged and your Arduino will be powered. But immediately as you remove power from this side, what will happen is this will act like a little battery, right? And you will have current flowing to the Arduino. Obviously it's directly connected. You'll have this resistor, right? Again, I recommend a value less than 50, less than 20. I'm using 10, it's fine, right? Everything above 5 should be okay. And if you're using small capacitors like the 22 microfarad one, you could, right, get rid of the resistor completely. I'm not sure it's enough, but it might, so who knows. Anyway, so what'll happen is you'll have negative here and positive here, and this will be acting like a little battery, right? So you'll have electrons going this way, right? It's fine. And then you'll have them also trying to go via the analog pin, right, to create a circuit, but they'll be hitting the diode the other way around, right? So the diode in this case is pointing to the positive of the capacitor, right? Before it was pointing to the negative, right? But now since it's pointing to the positive, you will have 5 volts between here and here, again quickly decreasing, but either way, and 0 volts, right, between here and here. So what you want to do is basically just very quickly read and notice that this is below a certain threshold that will accurately tell you that the power has been dropped. So let's say usually you should be reading, you should actually, and now that I'm looking at this, you should actually use a Schottky diode, I think it's the proper way of saying it, because that'll have a 0.3 or even lower drop, and so you'll only be reading 0.3 above your supply voltage, thus you'll be in your rating. If you use a normal diode, so 0.6, 0.7 volts, then you might actually add some resistor here to limit any possible damage, because you'll again be overloading your analog pin, because you'll have 4.5 here and 5 here, so you'll be reading 0.5 volts above your VN. But again, this is all details and it should work, right? So I mean, it's going to be fine even if you don't do that. And yeah, this is the more accurate way of doing it. But again, the other way is fine as well. So yeah.